So we have one new topic to cover. This is our last section, section 4.5. And what we're going to learn in this section is how to find antiderivatives using a technique called U substitution. And so let's look at the process here. U substitution is really sort of the analogous version of using the chain rule. When we took the derivative using the chain rule, we had an inner function and outer function. This is sort of the backwards version that we would use when we work with integration and finding antiderivatives. So let's look at an example here. We've got the integral of the function x plus 2 quantity to the 5th power. So what you're going to do when you do a substitution, do an integration by substitution, is you're going to select a substitution or replacement, and you're going to call it u. So in this expression, I'm selecting the inner function. Very often, or most often, the u that you're going to select is whatever's on the inside of something else. So if you think of a composition of two functions, the one that's on the inside is generally what you're going to use for your choice of u. So I'm going to let u equal x plus 2. And then the next step, you're going to take the derivative. So du dx, and I want you to use that Leibniz notation because I think that'll make this easier for you later on. Du dx is equal to 1. So in other words, the derivative of this function with respect to x is just 1. And so in the original expression, what your goal is you want to substitute everything that has an x, everything in terms of x's, you want to substitute for something in terms of u. So the x plus 2 I've already taken care of. The x plus 2 is going to be replaced with a u. I need to also replace this dx. So notice what you have over here. By taking the derivative of that u expression, I have du dx equals 1. And we can think of this as division. And if you think of this as division, you can multiply the dx to the other side. So 1 times dx, of course, is dx. So du is equivalent to dx in this expression. So I'm going to go back to the integrand. I'm going to make those substitutions. So the x plus 2 was replaced with u, so that turns into u to the 5th. The dx was replaced with du. So now I'm working with the integral of u to the 5th du. And remember earlier we said we call that a dummy variable. And again, it's because it doesn't matter what the variable is. But the point is I want to integrate now with respect to u. So use your power rule. You've got u to the 6th over 6. And then, of course, plus c because this is an indefinite integral. At the very end, you want to go back and make your substitution for u because our original goal was to integrate with respect to x. So I'm going to substitute back in u in place of x, or x plus 2 rather, in place of the u. So we have x plus 2 to the 6th all over 6 plus c. All right, let's try another. We've got the integral of the square root of 1 plus x squared times 2x. So think about what's on the inside. That's going to be your choice of u. The other way to think about your choice of u, and this is something I find helpful, is think a step ahead. If I let u equal this, its derivative will equal this, blah, 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 whatever. When you take the derivative, if that is also in the integrand, that's your choice of u. So think here for a minute. If I let u equal 1 plus x squared, what is the derivative of 1 plus x squared? Well, that's 2x, and that's already in your integrand. So that's a good choice for u. So I'm going to let u equal 1 plus x squared. I'm going to write du dx as 2x. And whatever's in terms of x, I need to substitute to be in terms of u. So this 2x dx is going to be replaced with du. Take a look at what I did. This equation right here, multiply dx to the other side. So 2x dx is equivalent to du. So now go back and make your substitutions. The square root of 1 plus x squared, if 1 plus x squared is replaced with a u, that becomes u to the 1/2. 2x dx, you just told me, was du. So the idea, the goal here is to make this into a simpler problem that you can work with. I can integrate u to the 1/2 du just by using a power rule. And that's the entire goal, is to take something more complex and make it simpler to work with. So using a power rule, the antiderivative of u to the 1/2 would be u to the 3/2 over 3/2, which simplifies to 2/3 u to the 3/2. And then just remember to replace your u with 1 plus x squared at the end. Let's try another one. We've got the square root of 4x minus 1 as our integrand. So what's on the inside of the function, that's going to be our choice of u. So we're going to let u equal 4x minus 1. Take the derivative of that, so du dx equals 4. Now what you'll notice this time is there's no 4 sitting outside of the radical like there was in that last question. You had the 2x sitting on the outside. So what we want to do instead is think about, I need to replace this dx right here. I have a replacement for the 4x minus 1. That's going to be u in a second. But this dx has to get replaced as well. So take your derivative expression and solve for the dx. If we do that, multiply dx to the other side and then divide by 4. dx can be replaced with 1/4 du. And that works okay because 1/4 is a constant. If you have a constant, that's an easy substitution. So let's go back and let's replace everything. So we have u to the 1/2, that's the radical, times dx, which got replaced with 1/4 du. And because 1/4 is a constant, we can put that 1/4 in front of the integral and ignore it, and just take the antiderivative of u to the 1/2. So the antiderivative is u to the 3/2 over 3/2, which is 2/3 u to the 1/2. I'm sorry, 2/3 u to the 3/2 times the 1/4 constant multiple. Clean that up a little bit. We get 1/6 u to the 3/2, and then make the replacement for u. So sometimes what you need to do is just ask yourself, what is it left that I have to replace? So in this case, it was dx that was left that I had to substitute for. So back here, I'm going to solve this derivative equation to get dx by itself, and that was what replaced the dx. Let's try this one. We've got the integral of cosine of 7x plus 5. So your choice of u is going to be what's on the inside, which is the 7x plus 5. So du dx is 7. And what else needs to be replaced? Well, the dx needs to be replaced. So I'm going to isolate my derivative expression for dx. I skipped a step here. Make sure you see it. Du dx equals 7 is what you should write next on your paper. Now multiply by dx, you get to this step. Dx is what I'm trying to solve for, so I'm going to divide by 7. Now go back and replace everything. So the 7x plus 5 is going to get replaced with u. The dx is going to get replaced with 1/7 du. The 1/7, of course, is a constant multiple, so you can ignore that. Integrate cosine of u with respect to u, and you get sine of u. And then, of course, replace u at the end with 7x plus 5. How about this one? We have the integral of x squared times sine of x cubed. So think about what's on the inside. X cubed is on the inside. So if we let u equal x cubed, think a step ahead now. The derivative of this would be 3x squared. Now that's not just a constant like it was in the last two examples. If it's a constant, no problem. Easy, we can work with a constant multiple, not a big deal. In this case, the derivative is going to contain an x squared in it. Notice that the derivative is 3x squared. But that's okay because notice in the original integrand we have an x squared right here. So what is it that's left that has to be replaced? The x squared has to be replaced as well as the dx. So x squared times dx is what's left to replace. So look at your derivative expression here. So you had du dx equals 3x squared. Move the dx to the other side. So now I have du equals 3x squared dx. But what is it I still need to replace? I need to replace x squared times dx. Can I obtain that from this expression? Yes, because I can divide by 3. So x squared dx gets replaced with 1/3 du. So now look at what you have. We've got sine of u times x squared dx got replaced with 1/3 times du. Now because the 1/3 is a constant multiple, I went ahead and put it in the front. And the idea is this makes it an easier integrand to work with. So the integral of sine of u du is going to be negative cosine of u times the 1/3, of course, and then replace the u with x cubed from the beginning. Let's try this one. We've got the integral of sine squared of 3x times cosine of 3x. So think about if I let u equal this, the derivative will contain this. It's tempting to just let u equal 3x. However, the problem with that is that would still leave us with a sine squared and a cosine expression, and we still have a hard time working with that. So I want you to remember, before you get too into this, that sine squared of 3x is equivalent to this, isn't it? Sine of 3x quantity squared. These are equivalent. So think about this. If I let u equal sine of 3x, what will the derivative contain? The derivative would require a chain rule. So the derivative of the outer would be cosine evaluated at the inner, which is 3x, times the derivative inner, which is 3. So du dx equals 3 cosine of 3x. Now look at what you've got. This cosine 3x dx is what has to be replaced. That's the remaining substitution. Can I obtain that from this expression? I can if I divide this 3 that's in the front. So now let's go back and make our substitutions. We've got the integral of u squared times cosine 3x dx gets replaced with du over 3, or 1/3 du. The 1/3 is a constant multiple, so I can move that to the front. Again, I want you to see the goal here was to make something very complicated into something easy to integrate. And that's what I've done. Now I've just got a straightforward power rule. So that gives me u cubed over 3 times the 1/3, which replaces with sine of 3x. The u replaces with sine of 3x, so it's sine cubed of 3x. Because of those 1/3, we get 1/9 as the coefficient. Let's try this one. We've got cosine squared x times sine x dx. This is very similar to the last question. Cosine x is the inner function here. Cosine x is inside of something squared. So let's let u equal cosine x. The derivative of the derivative of cosine will contain what? It'll contain negative sine x. Don't worry about the negative. The point is it contains sine x, which is what we have in the original integrand. So that's what we need for our substitution. So I need to solve for sine x dx, which means this negative has to go in the front. So sine x dx is going to get replaced with negative du. Cosine x got replaced with u. So we have u squared times negative du, and because the negative is like a -1 constant multiple, we can put it in the front. So we have negative u cubed over 3, which gets replaced with negative cosine cubed over 3 plus c. Let's do one more. We may see a couple questions in this section where they talk about differential equations again. We did this a little bit at the beginning of the chapter. So when we talk about a separable differential equation, that means we have a function, an equation with a derivative in it. So dy dx equals the product of two functions where one of them is a function of x and one of them is a function of y. You don't have to get too concerned about the notation, and you don't have to get too concerned about the term separable. That's not so important. What I want you to notice is when you see a question like this, the technique we're using to solve this differential equation. So dy dx equals 2xy squared. So this is in the form we need it to be for a separable differential equation because I'm multiplying a function in terms of x times a function in terms of y. So algebraically, what we're going to do is we're literally going to separate everything with an x to the side with the dx and everything with a y over to the side with the dy. So what I did is I multiplied by dx, and at the same time, I divided by y squared. And then what we're going to do is we're going to integrate both sides. So the left side is going to be integrated with respect to y. Now notice what I did here. dy over y squared I wrote as y to the -2 so that we can apply the power rule. So the integral of y to the -2 with respect to y is going to be -1 over y, or negative y to the -1st, right? Remember the power rule, that's y to the -1 over -1, which is where that negative comes from, plus a constant c. The other side, the integral of 2x with respect to x is x squared plus a constant c. Don't worry so much about these c's. It's not a big deal. The c's are generic, constant of integration. Whether I call it c1, c2, it doesn't matter. You can just stick the c on the side with the x's. That'll work just fine. But notice I took this y to the -1st. I wrote it 1 over y. And now when you do these problems and you're solving a differential equation, you want to solve for y at the very end. So that means I'm going to multiply the y to the other side, and then I divide it at the same time by the x squared plus c. And that would be your solution to the differential equation. Let's try this one. It says solve the differential equation. dy dx equals x minus 4 all over the square root of x squared minus 8x plus 1. Notice there's no y's here, and that's okay. That just means I'm going to multiply the dx to the right side. I'm going to leave the dy where it is. And when I integrate both sides, what you just want to think about here is I've got a 1 on this side. So what is the integral of 1 with respect to y? That's just going to give you the y, right? The antiderivative of 1 would just be y if I'm integrating with respect to y. Now on the other side, this is going to require a u substitution. This is what we've just been talking about in this lesson. So think about if I let u equal this, the derivative will contain this. What looks like it's on the inside of something else? Hopefully you noticed x squared minus 8x plus 1 is on the inside of the radical. So we're going to let u equal x squared minus 8x plus 1. The derivative of that would be 2x minus 8. I'm going to go ahead and multiply the dx to the other side. And what I want you to notice is what's remaining here that needs to be substituted. This x minus 4 dx is what needs to be substituted. I can get that from this expression if I factor a 2 out. So if I factor a 2 out, there's the x minus 4 dx that I need. Divide by the 2, and we can go ahead and make our substitutions. So we've got 1/2 in front, that's the du over 2, times 1 over the square root of u, because remember u went inside the radical, and the radical was in the denominator, so it's 1 over the square root of u, and then the du comes from the x minus 4 dx expression. Remember that was 1/2 du. So power rule, that's u to the negative 1/2. I want you to pause the video and work that out. That gives me u to the 1/2 over 1/2, which is 2u to the 1/2. So those 2's go away. And I'm left with u to the 1/2, which is the square root of u. But remember, u was x squared minus 8x plus 1. And notice I just brought that y down on the left side, and I put the plus c on the right side with the x's. Always for these differential equations, just leave the plus c where your x's or your independent variable is. Of course, the AP exam doesn't apply to you guys. So all we need to worry about is working with these u substitutions and practicing and getting good at these u substitutions so that we can find these antiderivatives of more complicated functions.